Hello, this is Roger Miller. Hopefully this video is finding you well. This is actually a second video, so I think I'm going to call it Chapter 2 just to keep these straight. First video went through and just kind of talked about a little bit of how the kind of the origin of the history of how, the original thought process behind some of these ideas. Originally thought was just put these videos out, let people take what I've been keeping cooped up in my mind for decades and maybe see if somebody else can take it to the next step. I think I'm actually looking at, as I'm starting to dig into these more and more, I think I'm actually making these videos more for myself to kind of revisit some of the ideas that I've had over the years and try to come up with a what my next steps are going to be. But again, if somebody finds something in here that they're interested in, definitely if progress can be made on this work, I would be fully in support of it. Like I said, just keep me in the loop. I love to hear what people are finding. Some of the other things, I think some of the stuff may be initially a little concerning the way I present the information. I apologize, or I just guess I ask for your patience. And I think at the end, hopefully at the end of at the video, you understand where my mind was and where it's coming from. So the initial ideas was that the whole idea was this fan was vibrating, and if I could control the vibration so that it was out of balance, if I could control the out of balance on one side, to be more out of balance on one side than the other, then I could actually get motion. The thought process here is that this is actually the propellentless propulsion, which is supposed to be a big no-no, but hopefully by the end of this video you'll understand a little bit more of why I think that it is something that is it's obvious and we should be working toward this. So the original inventions I used to build was made out of wood, metal, using rocks as weights, kind of deal, quite sizable. And one of the issues that I had was that these things would create a lot of force, and it, of course, rip themselves apart. So what I try to do is I actually come across these building blocks or building things called connects, and I found that I could actually build much smaller, manageable copies. So what I'm going to do is I'm going to show you like the first version. This is something I've had hundreds and hundreds of these things, similar things. So I mean the idea about a fan going around. And that's the the basic premise of this. The idea is that I'd actually create these, put motors on them, actually get foam, put these things, basically make a little boat for them, and have these things actually floating in a kiddie pool I fill up in my basement, and with a motor have this thing running. And the basic concept behind these is that let me see if I can find out where we're at right here. So here would be the up statement. So that would be up, where these would have these weights on it. So as the inner one is fixed, these would turn around, and again it's going to have one up here, and you'll notice there's 4 or 3 down there, the weights. So which means there's 3 times the weight down there versus the one on this side. One of the things when I started running these tests had issues. One is when you only have one, the base is going to want to spin in the opposite direction. So really hard to control when this is spinning at any type of speed. The bottom would have to do that. So I actually created a double one. One would spin one direction and the other one would sit on top of it, spin the opposite direction. That took care of the spinning, but the weight started to get very heavy, and the results were still inconclusive, I guess. As I'm looking at it, it's like, why am I getting, is there movement, is there thing? And one of the reasons why, if you take a look at this, as this goes through the air, there's wind resistance. And so that's one of the other things that I had to deal with, is that as this thing is spinning, it's going to have friction with the air, and that would actually be causing some movement that could be explained by that. Which it's like, okay, so I had to kind of set this aside, and I decided to start actually doing some running. And one of the things I used to log a lot of hours, many hours, and I used to listen to, at the time in the late 90s, I'd listen to like podcasts. I'd download podcasts and science podcasts, physics podcasts, and listen to them. One of the things that I also came across is, and this, I bought multiple of these books over the years. This is actually Einstein's own explanation of special and general relativity, straight from the man's hands. This was written in German, so it's translated to English, but I actually found a text version of English of that book actually on the internet, and I actually got a audio or a text to audio app that actually converted it to audio files. And so I actually burned those audio files, put those actually on it. One of my portable earbuds that I was using at the time, MP3 players, and I would actually run listening to that. And in that, there's an equation when Einstein was talking about the Lorentz transformations and having to do with special relativity. And this equation is the crux of it is basically why everybody hears that matter can't travel at the speed of light. And the equation in it, if I can remember correctly, it's 1 over the square root of 1 minus v squared over c squared. And basically what that means is that at very normal, everyday speeds, velocities that humans deal with, we can't perceive any change in the effort that's used to push an object. However, this equation says that as you increase increase the speed, as v continues to grow, it becomes more and more a percentage of c. What will end up happening is all of a sudden it takes more and more effort, and eventually and that's why we can say when v becomes c, it takes infinite amount of energy to push it to that speed. So when you're going from like 0 to 1% of the speed of light, the number is minuscule. Going from 2 to 3, again, the effect of special relativity is imperceivable to humans. However, once you start getting up in the 90% range, that's when we start seeing some actually significant forces that are being required, like the Stanford Linear Accelerator. I mean, it generates 90 plus % the speed of light objects, and it takes a lot of force to push these protons and particles at these speeds. Hearing that made me realize, and this is going to be one of those things that I'm going to say it and be written off pretty quickly, is that equation actually could be a hall pass to the second law of thermodynamics. And basically that throws out the second law of thermodynamics is why there can be no endless it's a machine that runs forever, that there's always going to be force. You can't get more energy out of a system that you put into it, and that's true. But there's things that you can look at that actually, when we start talking about special relativity, I think is one of those things where, let me explain it this way. So right around that, after I read this and realized that has something, that actually could impact what I've been trying to do, I reached out to and I found a professor, I think at Cal State Fullerton, Professor James Woodward, which was doing some similar things with what I was looking at. He was his was definitely different than what mine was, but I wanted to do it mechanical, and if I remember, he was more of inducting currents through objects to increase their mass. But in working with him, I actually came up with a a thought experiment, where, and again, this is 100% thought experiment, so I'll go through that real quickly with you, and then we may leave it to the next video. I want to try to keep these short as possible in the next video to actually start going through some of these inventions and explaining. Anyways, I call it the atomic pop gun. So none of this is mechanically possible. It's just one of those thought experiments. So you're in space. You have your spacesuit on, and you have a normal pop gun. And what a pop gun was, I think in the 1950s, it's basically it looked like a rifle that had an air chamber that had a cork with a string hooked up to it. It had a cork at the end of it. And the reason why they call it a pop gun is that the air, you'd have high air pressure inside the barrel, and you pull the trigger and release the cork, and the cork would go flying out and make a popping noise. So for this thought experiment, you're floating in space. You have your location firmly identified. You know exactly where you are in space relative to whatever you're going to use as a reference. And you fire the pop gun. Now, this is a special pop gun. This pop gun will actually shoot this cork out at 100 kilometers an hour, and the cork itself actually weighs 1 kilometer, or weighs 1 kilogram. So when and you're 100 kilograms. So you shoot the cork out. The cork goes flying in one direction. Newton's laws say equal and opposite reaction. You're going to fly in the opposite direction. So that 1 kilogram cork is flying at 100 kilometers an hour. You're 100 kilograms. You're going to fly in the opposite direction. You're going to be pushed back in the opposite direction at 1 kilometer per hour. So not very fast. You're just going back. The cork goes to the end of the string and stops, and then all of a sudden both of you stop. You look at your location. It's like, yep, that's exactly what you expected. You expected, for whatever the distance was for the time, they match up. The 1 kilogram equal and opposite reaction. So then you pull the string of the cork back in. As you pull it in, you're pulling in just normal speeds, and then you put the cork back into the pop gun, and then you look at your location. You are exactly where you started out. Okay, everything Newtonian physics makes sense. Everything falls in line. But you want to do something a little bit more dangerous. You've read online where you can buy this atomic pop gun. I call it atomic pop gun because this pop gun is so advanced that it'll shoot that cork out at 90% of the speed of light. Again, not physically possible, just using it as a thought experiment. So you take that up into space, you get the same location you started out, you shoot that pop gun, boom, boom, it goes in and it stops because it's traveling so fast. And you moved in not equal and opposite direction, or an opposite direction. But what you realize is it's not equal. For some reason, you actually moved over twice as far away as you did when you used your normal pop gun. String's the same length, everything. The mass is the same mass. So you're thinking, that's strange. So then you pull that cork in and put it in the gun and realize you're not where you started out. You're actually at a different starting point than when you first shot it. The reason why that is, that's what special relativity tells us, is that when that cork is sped up, the force needed to push that cork out at 90% of the speed of light, it's not 1 kilogram of mass. I call it the relative mass, but I'm sure physicists out there are going to talk about all the actual terminology. But the relative mass of that cork wasn't 1 kilogram. It was actually like 2.3, 2.4, some number in that range. Because when you take the 1 over the square root of 1 minus v squared over c squared, when v is actually 0.9 of c, it is a significant change. And if you get even closer to the speed of light, you can actually get higher, and you can actually get more and more results. Now the thing is you're not going to be, once that cork gets to the end of the string, it stops. Both of you, it's going to stop both of you. So it's not like you can just keep on, firing it and your speed will increase, but your location will change. And that's the whole concept around what I've been working on. And I'm going to go ahead and I guess one more thing here is the some of the equations that I was working on. I was actually right around the end of the 90s reading about the Voyager spacecraft, how it seemed to be slowing down. And I thought that, and scientists couldn't answer that. So I actually reached out to NASA. They put me in contact with the person that's was responsible for doing these calculations, and exchanged a couple emails back and forth with them. And it's like when you actually take one of the things that they did to save money, as opposed to using gyroscopes on the Voyager, they decided to have the whole apparatus spin. Well, that large distance and the spinning, you can actually do the math using this equation that I talked about with special relativity, and you can actually come where the mass should be varying by with very close to the amount of what they were seeing as their discrepancy. When you start taking about the spinning of the apparatus along with the speed of it actually going through space, so it's actually doing a corkscrew distance, you can actually measure that out and see that the masses are actually greater than what they were thinking should be, and so that's why it would not be moving as fast as what they thought it should be. So anyways, it was something that was kind of interesting, and that's going to lead me to my next video. Thank you very much. Hopefully you're doing well. Take care. Bye now.